So today we are going to look at the formal definition of a limit. And this is something that we really haven't actually looked at. We've dealt with it on an informal basis. And the thing about limits is that it kind of feels very imprecise. But as we'll see, we can actually very formally define it in a rigorous way so that it's not just this nebulous thing, but that it's actually real. So we're just going to jump right in and look at this definition. I do warn you, this can be a little bit confusing. So it might be helpful to really think about this and let it sink in so that you can understand it. So the definition of a limit says that if we define a function on some open interval around x equals c. So we're basically putting c here and we're defining some open interval around it. But the function does not necessarily have to be defined at c. It can have a hole there or any other type of discontinuity, mainly a removable discontinuity if you want the limit to exist, but that's allowed. Then we're going to say that the limit as x approaches c of f of x equals L if the following holds true. Okay, basically we're saying that for all epsilon, so we typically use the Greek letter epsilon traditionally to define this, then there is going to exist, so again that means there exists some delta, so this is the lowercase Greek letter delta, greater than 0, such that basically this inequality will imply that that inequality is true. So let's actually try to break this down with a graphical example here. So this is a particular function that, before this definition was given, we would have been able to conclude the limit as x approaches 4 of this function is equal to 2. Okay, that should be obvious based on the statement. So what does this actually mean? Well, what it's saying is that if I were to consider the value 2, which is the y value, you'll notice that epsilon is associated with the y values, and delta is associated with the x values, so keep that in mind. What it's saying is, well, if we define some interval around 2, so that, let's say we take 2 and then we take 2 plus epsilon. Again, epsilon is just a number, and we take 2 minus epsilon, and I basically look at the function between those 2 points. Then basically I'm going to be able to construct. So this is kind of the given here. We're assuming that we have this interval here. Well, then what we're guaranteed is that we can define some x interval around the point 4. Again, not including 4, but around 4. So this is going to be 4 plus delta and 4 minus delta. And if we create these vertical lines, what we desire is for the entirety of the function to basically be between the bottom line and the top line. So notice that everything inside of this interval is going to be in there. We could have chosen a different delta. For example, we really could have chosen to anywhere except maybe about like right here, where the line crosses that particular point. So how does this actually encapsulate the notion of, as we get closer and closer to 4, the function gets closer and closer to 2? Well, the key here is this notion that this is true for every epsilon greater than 0. So in this particular example, we let epsilon be about 0.5, which is one possible choice of epsilon. But we don't actually have to choose that. We should be able to do the same process if we choose a different value of epsilon as well. So let's say I made it smaller, for example. So I make my band here, and I make my band here, and I make a smaller interval. The question is, well, can I still find a particular interval down here where everything is except this point in the center is in between? And the answer is yes. So notice we're going to have to choose a smaller delta interval, but I can still construct an interval in which everything is going to be between, everything between these two lines is also between these two lines. Everything is kind of inside that box. And then you can keep going. Well, what if you choose a smaller interval? What if you choose a smaller interval? And you zoom in. If that's always the case, then the limit will exist and be equal to that value. So this allows us to encapsulate the closer and closer to idea of a limit. Keep in mind that even though we weren't dealing with limits this formally last time when we introduced it, this is still the same idea, okay? This isn't a new idea. It's just the same idea formalized into this epsilon and delta limit. Now, in some calculus classes, proofs are done to actually demonstrate that this limit exists, but that's a more advanced topic, and maybe I'll eventually make a video that goes through some of the ways in which you can prove it. Obviously, in higher level math courses, an analysis where you want to formally show that limits exist, this is the way in which you want to do it. But especially for those who aren't pursuing a math major, this isn't particularly important to know how to prove it, but it is useful to show that this is something that can be rigorously defined, even though a limit doesn't feel very rigorous when you first deal with it. So that's all for this video, and as always, take care.